Microsoft Research again with Jim Laris and Galen Hunt, and these guys have written a managed operating system as a prototype. Thank you. This is great. So what's going on? What is Singularity?
Well, first of all, who is who?
Oh,
this is my famous question. That's the only question I get to ask, right? Who is you? Who are you?
I'm Galen.
Sorry.
No, he's Galen. I'm Jim Laris.
Great.
I'm Galen Hunt.
Cool. And what do you guys do here?
We're researchers in Microsoft Research.
Awesome.
I do programming language and programming tools.
And you've been on Channel 9 before, right?
I've been on Channel 9 before. A couple of months ago, you guys came in.
Veteran.
And I've never been on Channel 9 because I do the really boring stuff underneath that, which is the operating systems.
Oh, that's not boring. So you guys, I always ask, like I remember I interviewed Christopher Brum, one of the first interviews we did. I was like, do you think a managed kernel is possible? And he laughed. In a industrial strength operating system. And then I heard about this little project that you guys are doing where you actually built basically a 99% managed operating system, which means you have a managed microkernel, etc. You guys did it. Can you talk about Singularity? Can you talk about challenges of writing a managed operating system, etc.?
Well, so
Talk to him. The camera's not here. There's just 100,000 people watching.
So it has been done before.
It has been done before.
So if you go back to like the Cedar and the Smalltalk projects at Park 30 years ago, they did build operating systems out of managed code. Okay, it's not exactly the same as the managed code we have today. So it's not a completely never been tried concept before. Okay, but the key thing in prototyping this through was that we said, well, there's a lot of great things about managed code, but maybe we can distance or create a separation between what is the current implementation of managed code in the CLR and what do we do way down in the bottom of the kernel, right? And so we built a prototype of a new managed code environment at the bottom of the system, and that's what makes it possible. So, for example, at the very bottom of the system, you've got to worry about how do you do garbage collecting, how do you schedule that garbage collection from the perspective of the whole rest of the system. And one of the things we don't do, for example, we don't JIT code down at the bottom of the operating system, because the last thing you want to do when you're taking a page file is say, oh, I think I'll go JIT some code up or something.
So probably a good question to ask is why would we want to do this?
Yes.
Right. So we sort of saw this as the managed code as a technique to help us build a system that was going to be more reliable than the systems that we're used to today. I mean, that's really what the big picture of the project was, is that not only did we want to sort of program it in a better language and try to avoid some of the errors that you get when you program in C, we also have been thinking about the system in a whole and trying to come up with a better structure for the system, a better architecture for the system that would lead us to build more reliable software. I mean, that's really the big picture goal, and certainly managed code is really important to that. But if we just sort of sat there and wrote a conventional operating system using managed code, we would get rid of some number of bugs. I mean, hopefully there wouldn't be a lot of buffer overrun attacks on this kind of system. But that wouldn't really solve all the problems. And so managed code is only one of the techniques that Singularity is trying out. So we're doing things like trying to build much finer grain isolation into the system. So we have a notion of a software isolated process, which is a protection boundary around a piece of code that can be used on a much finer granularity than a conventional operating system process, which is a pretty big, heavyweight, hardware enforced abstraction in the system. So you really, you've got to get the page table set up right. You really got to sort of go down into the low level guts of the hardware to enforce that. In our case, we're saying, let's come up with a lighter weight way of isolating part of a system so that we can wrap this around, for instance, extensions, device drivers, extensions to programs, extensions to the operating system, and really sort of keep them in these self-contained units so that we can put them together into the system without having them be able to interfere with other parts of the system, either maliciously or accidentally, and so that we can end up building a system that is much more fault tolerant. So we don't really expect to build a system where nothing fails. we expect to build a system where when things fail, we can really sort of see what's failed, clean up very quickly and reclaim the resources and continue operation. Not without sort of any kind of transient, but without the system as a whole coming down and blue screening or something like that.
And so, in other words, you're saying that process X can't overwrite process Y's memory. There's no notion of shared memory in your system.
Absolutely no shared memory in our system.
Okay,
So,
which is a major problem that we experience today.
Right.
On some levels, I mean, I won't say a major problem, but it's a hard problem to deal with.
it's a hard problem, right? I mean, people want shared memory because it makes programming easier, and then they don't sort of think about what the consequences are. If you have two processes on a conventional operating system that have shared memory, and then they're sharing data along fine, and one of them dies.
Mm-hmm.
Well, what's the state of the shared data? I mean, the other process is still there; it still can see the data, but it has no idea whether it's consistent or not. And at that point, there's not really much that process can do except to say, I really should terminate because my world is left in an inconsistent state because of this other process failing. And so then, the failure propagates in the system because of the shared memory. And we're trying to build a system where that doesn't happen, or at least doesn't happen very often, that the failure of one process would cause another one to terminate.
Interesting. So when did this project start?
18 months ago?
Yeah, about a year and a half.
About a year and a half.
So and how long did it take you to get the prototype up and running?
About 18, no, about 17 and a half.
So it's actually running right now and it's relatively stable.
Yeah, it's
Yeah.
relatively stable.
Yeah, I've actually gone out and given talks and had the slides come off of Singularity. So I actually run Singularity to do the talk. Now
Wait
we
a
don't
minute.
run PowerPoint. Okay. So here's the clever hack of this, right? So this is a prototype system, right?
Yeah.
So we don't run PowerPoint. What we do is we take the bitmaps from the PowerPoint slides and compile them into the kernel, and then display them onto the screen. Okay.
You could imagine something, a slightly more elegant solution. but it shows that we have enough confidence to get up there and give an hour-long talk, and it's not going to crash.
An hour-long talk, and it does garbage collections while you're doing it. It's it's
Mhm.
doing all the managed code stuff, and it stays alive for an hour while you do the presentation. And in fact, you don't fear that it's going to crash while you're doing this. And one of the interesting things about it, so the device drivers that keep the screen driver that's drawing the bitmaps to the screen, that it's reading out of byte arrays out of the kernel, is a type-safe device driver. Okay, it is safe C#.
And so no blue screens are possible.
There's no blue screens possible with this device driver. The keyboard driver is the exact same thing. It is C# code, totally safe, and it's taking the interrupts and passing them. And they're talking to hardware, and so we protect. We insert code that does bounds checkings on the access of the hardware.
Do you have this
things
one
like
running on one of your machines right here?
Well, you didn't tell me you wanted to do a demo.
We'll see.
The user interface is nothing to write home about.
You haven't got Arrow running on it yet?
Yeah, we have
DOS.
a little bit. If you've seen DOS, it looks very familiar, right? But this is one of the key things about doing a research prototype is, there's this old adage when you program that the last 10% of the program takes 90% of the time. Well, the key thing with research is we don't do that last 10%.
Exactly.
We do the first 90%. We do the thing that will let us prove. So, we come in this with some radical ideas. We say we're going to build a system all out of managed code. It's not going to have any shared memory between the processes. The processes are closed in that you can't load any new code into them. We also say that the processes can only communicate through these special channels, communication mechanisms we call channels, that have a contract that says what the messages look like and what the order of the messages are. We made some fairly radical decisions that to a product group we'd say, do we dare do this? What's going to do to compatibility and everything? We say, we don't care what it does to compatibility. We're going to go off, we're going to explore this new space, figure out what works well, and then, based on that experience, then we go out and inform our colleagues in the research community outside of Microsoft about, here's where we go, this works, what worked well, et cetera. And also be able to inform the product groups and say, hey, maybe you should go look in this direction because here was our positive results.
Right. So we have no illusions that we're building an operating system that Microsoft is ever going to ship as a product. That's not our goal. I mean, particularly we started with the idea of forgetting about compatibility with any existing system, which means that almost nothing runs on this because the interface is very different. And, you know, it has the disadvantage that it looks like DOS, and it's going to look like DOS for a long time, and we're not going to have any really fancy applications that can show it off so that you know, want to put it on the screen. But it also has the advantage that we can really experiment with the structure of the system and what it looks like, what an application actually looks like on the system, without worrying about sort of, well, we can't do that because we wouldn't be able to have the Win32 or in a similar interface if we did that. You know, for instance, we have been very much trying to make the code on the system much more self-contained and static. So Galen mentioned that we don't allow dynamic code loading, so that, you know, when a process starts up, that's all the code that's ever going to be in that process's object space. And, you know, that has a lot of advantages for people that are doing compilers and optimization. We don't have to worry about somebody, you know, coming in and loading some code after we've done the analysis to figure out what's going to run in there, so that the compilers can generate much better code, and the program analysis tools that find bugs can be much more accurate. But, you know, it also means that the programming model that everybody's familiar with, which is, you know, a DLL or dynamic code loading, doesn't work on the system. And so, you know, if you don't worry about compatibility, you can think up new solutions to that, which is really what we've been doing, saying, you know, if you want to do an extension to the system, if you want to do an extension to the application, start up one of these lightweight processes and communicate with it over a channel. And, you know, the interesting thing is we're actually using exactly the same model from the system and for the application. So device drivers run in these software isolated processes, communicate over channels to the rest of the system. If you write an application on Singularity, you use exactly the same mechanism. And that's one of the things that we're able to do because we don't have to worry about backward compatibility with device drivers or backward compatibility with application codes or APIs or anything like that. But, you know, if you were actually going to go and build a product, but these would be the wrong decisions.
Absolutely. I mean, and now the architecture you guys chose is the microkernel.
Yeah.
And today, most industrial strength are macrokernels, monolithic kernels, whatever you want to call them. So can we say that in the future of operating systems, probably going micro might not be a bad idea? Or let me rephrase this. How long? I mean, are we always going to have a monolithic model? That's my question. I mean, you have Linux is like that, Windows is like that, the Mac is like that, blah blah blah. At some point in time, do you think it would make sense to actually have a commercial operating system that is re-architected to that degree?
Well, so we certainly advocate this position. And if you look at microkernels were studied 20 years ago, right? And there were two kind of fundamental issues with microkernels. One of them was performance, which is, you know, you move all this code into separate processes, and now you have the context switch time of moving between processes every time that you have to go between and break things up. And so there were big performance overheads, okay? And that was probably that was the immediate thing that caused problems and made it not very commercially viable. And the other problem was programmability. You know, how hard is it to reason about communicating between these processes? I can't just go share a couple of variables. I have to actually send a message back and forth. From the performance side, one of the interesting things with using managed code is, as Jim mentioned, we call them software isolated processes. So normally, when you have processes in an operating system in other microkernels, the protection mechanism is hardware protection. You have these protection domains that use page tables and other things in order to secure one process from the other. Well, in our system, we can guarantee, because of type safety, that a process can only point at pages that it actually belongs to it. Okay, in fact, it can't create either on purpose through malicious intent or accidentally get a pointer off to some other page in the system. Okay, and so because of that, we can run all of the processes in a single protection. Okay, so we don't have these context switch times that you have in the system. Okay, and so we can talk about having context that our message passing can be on the order of magnitude faster than what you could do in any other system. Okay, because it's all managed globally. And we can start up processes much more quickly because we don't have to go create a page table and flush TLBs and do a bunch of other things. And so the performance side, the early performance numbers look very, very promising. That old reason for not doing markup kernels, which was performance, doesn't exist anymore. And then the question is about the programmability. Tools, well, that's where Jim's team comes in. This is why Jim and I got together to do this project, because the tools guys have made phenomenal success in the last couple of years of progress. And so we can talk about being able to check the boundary between, well, I should let Jim talk about the great things his tools can do, but we can check how the programs communicate. And one of the things it kind of gets to is, there's a point that Jim articulates, which is that prior OS development and prior OS innovation has been driven by advances in hardware. Moore's law was increasing the performance exponentially, and so there was always new opportunities to try out new things with software. Well, perhaps the most revolutionary thing about Singularity is it is a new operating system innovation, not driven by hardware, but driven by software, driven by the tools.
Fascinating.
And what we can do with the tools.
So driven by the CLR, in a sense.
Driven by managed code. We don't actually use the CLR, but we use C#. We use our own variant of C#. Our compiler takes the MSIL, the same MSIL as the CLR, and generates code from that. So it's very similar to the CLR. We use an infrastructure that was built inside research called Bartok, which is a smaller, lighter weight version of the CLR, which is easier to work with than the entire CLR project.
I'm sure you don't need Windows forms,
No.
system.xml,
That's right.
etc.
Right, and even then we had a fairly minimal library to start with, and we found that we could strip out a lot of it and save a lot of space. There were a lot of places, for instance, in the kernel where we didn't need XML. We didn't need 5 different languages and the ability to compare strings in different languages to each other. And so there's a lot of generality there, which is incredibly valuable for developers. But it has a cost in terms of sort of runtime overhead. So a lot of what we've been looking at in terms of the tools are ways to generate code that's efficient for managed code. Because when you're starting at the bottom and building up on top of it, you want to get efficiency. I mean, it doesn't necessarily have to, be better than C or C++, because you're getting other advantages from using managed code. But it has to be competitive. I mean, if you're an order of magnitude slower and an order of magnitude bigger than, your C program, then when you start talking about the kernel, that can be a serious problem. So a lot of what we've been doing is focusing on optimizations, ways to sort of factor things to be smaller and to be tighter, ways to build very lightweight abstractions into the system, where we don't use hardware. And so in some sense we sort of get past the C guys who really couldn't follow us down this path because C is such an unsafe language. You can construct pointers, and so you really have to have hardware protection if you use C. And so because the language gives us this safety guarantee, which we can check, we can do things that they couldn't do in C and C++. So we can actually be faster than they are for a lot of operations, which is kind of funny because everybody thinks of C and C++ as being faster, but it's only because you're comparing it over here. And if you say, well, no, the game's shifted and we have all these other techniques that let us run without all of those expensive hardware mechanisms, then the game's over here for C and for C# and other managed languages, and so we can actually do things that they can't do, which is what Galen was referring to, is that this is really a project that's being driven by advances in terms of managed languages, compiler technology, the ability to check the safety guarantees at runtime, which is called proof carrying code. And so we're really using that to sort of say, let's see what the consequences are in terms of system structure. I mean, the overriding goal is to build something that's fundamentally better, more reliable. But the way we're doing it is by saying, let's take advantage of the software technology that's grown up in the last 10 or 20 years.
Absolutely.
And do something different with it.
And I'm sure that, not that this is going to happen, but I'm sure that the product team, if anything, could learn from you how to build a runtime environment to actually put down in the kernel, right? So I know there's people on the driver team. In fact, I've interviewed them, and they'll be on Channel 9. Someone who's really, really passionate about having management in the kernel because no blue screens, easier to write, easier to debug. You have real exceptions, etc. So you probably have already worked with these people. But I mean, the point is that's kind of an immediate sort of product team.
Well, just to put in a plug for research, that's
Yeah.
really what research is here for us. We try out new ideas where we do the crazy things that you really wouldn't want us to throw a whole product team after. And we figure out what works, what doesn't work, and then we work with the rest of the company to transfer the really good ideas into practice.
Fantastic.
So, yeah, I mean, this is, classic high-risk research. We could fall flat on our faces. It could turn out that the operating system didn't work, and it was really slow, and there's nothing we could do about it. Fortunately, it doesn't look like that's happening. But, you wouldn't have wanted to start off with, a 30, 40-person product team going down this path until you had some idea that it was really going to work.
Yeah.
Do you think Microsoft could ever do a new operating system from the ground up? Because I think about that. I think about how many thousands of people are working on Longhorn, right? And how, like you mentioned, all the constraints that go into a real OS today, where at least most of your apps have to run on it. And everyone that doesn't gets written up everywhere. You won't, look at Apple when they did OS 10. Quark Express won't run on OS 10, and it took 2 or 3 years for that. Just that one app to get ported over to OS 10, really. And do you think Microsoft could ever rewrite it from the ground up? And what would
It seems difficult, right? I mean, the compatibility is such a big issue in terms of an existing operating system. I mean, people buy it because they can run something on it, not because it's a wonderful operating system, and they just sit there and look at the operating system. So, if you get rid of the reason why people want an operating system, which is to run their applications, then you pretty much undercut the reason for the system. So, I think in the commercial side of things, you can't really sort of evolve an operating system by rewriting it.
Sure.
The compatibility is difficult to maintain. And, there are very few examples of it actually happening on a large scale. I mean, I guess Apple's done the best job of it, but it was painful for them. And we did the same thing, I guess, with moving from 9X to NT.
Completely different kernel
And
architecture.
think about how long that took.
Yeah,
The numbers have been cited. It took 14 years from the day we hired Dave Cutler and his team to the day that Windows XP shipped as the platform for the company.
Mm-hmm.
And so,
But they were able to pull it off, right?
With a
It took
good
14 years.
I remember I was an NT beta tester.
But the type of-
this stuff doesn't run.
I would only argue that the type of things that you guys are talking about could potentially be added, underneath the covers, whereas those of us up in the application world and don't even notice it, right? Just because you have a managed kernel, what does it mean to me, the application writer? My application is still going to work. Maybe I'm going to have safe processes. But the execution model you're talking about, that's
Right,
a different story.
That would be very different.
Yeah.
But in the kernel, it does matter. You talk about device drivers, right?
Mm-hmm.
And one of the strengths of Windows is that there's a huge number of device drivers. Pretty much any piece of hardware you buy, you can find a device driver for. If we change the kernel, either those device drivers are going to work or someone's going to have to rewrite them.
Yeah, sure.
And that's a hard compatibility model to preserve because it really exposes the guts of the existing system.
Absolutely.
Do you think this OS could eventually be used in a different kind of device that we don't envision today, or something where
Sure.
compatibility does, like Spot Watch, right, came out with a new OS paradigm.
Yeah. Yeah, I think, somewhere in that space it probably makes a lot more sense, but if you don't have the compatibility, and you probably also need some constraints that would, argue against using a more conventional system, one that's already out there. It's hard to know, right? I mean, people are coming up with all sorts of hardware and trying to push it in different directions. You never know what's going to, the connections that are going to appear.
And again, you guys aren't a product team.
Yeah,
You're pushing
yeah.
the boundaries.
Yeah,
That's checking cool things out.
So at the end of the day,
Yeah.
whether you take the Singularity code base and ship it in a product, is not the yes/no question of whether we were successful or not, right?
Mm-hmm.
What we ultimately try to do, there's a whole bunch of different solutions, different points of technology transfer that can come out of this. We talk about some of the stuff we've done in working on reducing the managed code library footprint, right? Well, you can imagine some of that maybe someday getting into how we build the CLR. And there's all sorts of different technology transfer points.
Mm.
That, you know, largely that's how we determine whether we're successful. It's, we come up with ideas that are valuable. The people who are doing the real work,
Yeah.
you know.
Does this process help harden the existing, are you able to roll back into C# or CLR some ideas that came out of this? Is that?
Still a little early to do that, but I mean, you know, we're experimenting with the language design as well. I mean, that's one of the other nice things is that we can change C# in various ways to try to put some new constructs in it to support systems programming or maybe to support the message passing communication. And we can see whether they work in a fairly realistic context by writing code ourselves and having, you know, other people involved in the project writing the code. And if they are good ideas, then, you know, certainly we will go to the C# team and say, look, you know, we've tried this out. This seems like it has a lot of advantages. You know, can we get it into a future version of C#? But, you know, language change is very slow.
Yeah.
Right? I mean, we don't bring out a new version of C# all that often.
Mm-hmm.
And, you know, we think very hard before we stick something in there, because once it's in there, it doesn't come out.
Yeah.
Well, generics is a great example of something that was driven by research.
Well,
Right? You
yes,
guys had-
yes. I mean, the ideas for generics certainly came out of the research community. The generic implementation was done by Don Syme in research.
Mhm.
And, you know, that's a great advance in the language. It really makes programming C# a whole lot better than it was before.
True.
But, you know, again, it was a long process, right? It took a number of years to sort of build the implementation and show that it was feasible. I mean, you know, before they decided to put it in the language, Don actually had to build it and show them that it was practical and that, you know, it didn't have bad consequences for the rest of the language. And then, it, you know, at that point, it starts becoming reasonable to think about whether this is the way you want the language to evolve when you know that you can do it. And, you know, we're sort of in the stage of demonstrating the feasibility or, you know, being able to at least quantify what the advantages and disadvantages are of this approach that we're taking. And, you know, that's the beauty of Microsoft Research is that we can do stuff like this. We can try things out, and then, you know, we have pretty good contacts with the rest of the company. And so, you know, things that we think are good ideas, we have the potential of getting them into products and getting them out from Microsoft to the rest of the world, which is, you know, pretty exciting.
Absolutely. It's amazing. I mean, it's great to see that operating system research isn't as dead as I had initially thought it was. I mean, I wrote something on my blog post. On my first blog post was like, what happened to OS research? We have these 3 commercial operating systems, but of course there's dozens of them out in the research world. But it was nice to see this thing on MSR website, Singularity. And then you had mentioned it in one of our discussions, and I was like, wow, excellent.
Well, there's 600 OSs out there that the virtual PC team knows about. So.
Fantastic. Wow.
I guess there's
They support
601 now. Have you tried your stuff on virtual PC?
Yeah, we do a lot of development on virtual PC. It's easier than having to boot it on bare hardware.
Yeah. What would you? What are you proudest of? What, you know, if you had another, if you had a guy from another company or MVP, that's a typical question.
Oh, what are we most proud of?
To the boots and rides. No, it's not. It's not. That one's pretty good.
That's what I was most proud of. That we built it, and the first performance numbers, which we needed for paper, so they were like the last performance numbers we could collect before the paper, were actually very good. I mean, you know, we had like a day before the paper deadline to get all the numbers that, you know, by just getting the stuff to work. And the numbers were good enough that we could submit the paper and feel pretty happy about it. And we hadn't done any performance tuning. It was like
Jim exaggerates. We actually had 3 days. A whole 3 days.
a whole 3 days. It sounds better at 1 day.
The process creation part.
You have future in marketing when you start exaggerating the numbers.
It seemed like 1 day.
It's true. We had a lot of debates. You know, it's been 18 months getting to this point. We had a lot of debates in the group about, you know, whether this is the right way to go or whether it's the wrong way. And, you know, well, it's going to be faster. I don't know, maybe. Is it going to be slower? You know, there were a bunch of open questions when the system finally ran. And the numbers were very, very good.
So now, what were some of the biggest challenges you guys had in making this managed operating system? And what are some of the what are some of the hurdles you guys had to get over, or maybe still haven't gotten over yet?
So one of the sort of the big picture hurdles is that this project involves people from a bunch of different areas, right? And, Galen is an operating systems guy. I'm a programming languages and compiler guys. And, we had to, the only way that this project ever got off the ground and got going is because we're in research and we could get, a bunch of compiler people and a bunch of language people and a bunch of tools people and a bunch of operating systems people to sit down and get excited about spending a fair amount of time building this system and to think that this is something that they wanted to do with their research cycles. And, that was really the big challenge because if we were just in one of these areas, I probably could write an operating system, but it wouldn't be a very good operating system. And Galen probably could have gotten some managed code running, but it wouldn't have had a good compiler. And, we wouldn't have been anywhere near where we are now, and we wouldn't have been able to sort of push the boundaries without the other people involved who sort of came in and said, well, we could do it this way, and, we have the technology and we have the software already that you can build on. And to me, that's the sort of the really impressive part of what we've accomplished so far. We have a bunch of goals in terms of sort of demonstrating that we really are going to make fundamentally better software. We haven't gotten there yet. But what we have done is we've gotten a big project with a lot of different areas off the ground. We've tried out some really innovative ideas, and they seem to work. And we're going to keep pushing and seeing how far they can really go now.
Fantastic. So how big is the team? Just out of curiosity.
How do you
Are we
want
allowed to talk about that?
Sure.
Sure.
It's hard to count.
Yeah,
So is it worldwide?
It is worldwide. We have people here in Redmond and in Silicon Valley and also in Cambridge, England, working on the project. Depending on how you count it, we have people from 11 or 12 different research groups.
Wow.
Inside MSR. It's the largest cross-group collaborative project that's ever been done in MSR. In terms of the number of groups that are involved, depending on how you count, there's a core of about a dozen people that are very passionate every day. I'm doing Singularity kind of thing, right? And then, but there's a number of other people. As researchers, we basically can do whatever we want on any given day, kind of thing, right? And so there's about
Now there's a job for you.
there is a job for
But
it.
you guys have to publish papers.
People
Right.
do evaluate you on what you
do.
do. It's not just like you can do whatever you want. Nobody cares.
But on any given day, but there's about 40 to 50 people involved, and they're phenomenal people. It's the best. The thing I love most about this project is, we're doing really cool technology stuff, but the people are just absolutely phenomenal. They're world class. And then there's me. They let me in the team too, but
Come on.
I write all the bugs. That's why they.
Right.
So,
Someone's gotta produce
we got to
bugs.
be able to produce the bugs so we can check them and see how.
Now, can we have an OS that it's impossible to write a bug in?
No.
But in a
It's a really small OS.
One line of code.
And then shuts down.
Down, right?
So I wanted to ask this question. You mentioned 11 different groups. One thing I've always been curious about this is building artificial intelligence, machine learning into an operating system so that an operating system learns about itself and grows and matures. And clearly we're far from that at today's day and age, but are you guys working at all with the artificial intelligence, machine learning folks? Are they part of the, maybe that's the next, I mean, is that even, is it too science fiction, or what I mean is like when you talk about like processes and stuff, an operating system that is able to understand when a process is just going crazy, and it knows that this was a set of circumstances, this is the process, I shut it down, I remember it, I learned from it, and maybe actually even be smarter than that with AI kind of stuff.
Right. Well, that's perfectly plausible with the machine learning technology that we have. We could certainly push in that direction to actually, have the system be much more aware of how it's behaving and, be able to compare it to past behavior and make some predictions of it. We haven't gone that direction yet. I mean, we're sort of, we're in a much earlier stage of building the system. But, we've certainly had that kind of discussion with the machine learning people about software tools and software itself. Right? I mean, there's a lot of opportunities to actually look at the software and apply techniques like that and sort of say, well, most of the time when we've seen this before, it led to that.
Yeah.
And, I think that's a nice direction to go in, and that's certainly a discussion that's been going on inside research for quite a while, how to use machine learning
Yeah,
techniques.
and there's been some other projects outside.
Yeah.
True. I mean, like a truly homeostatic operating system. would be very interesting. You know?
I don't even know what that means.
Well, Charles does this to me all the time. I'm going, what? Simplify it to...
Okay, well, that's like your oven, right? You turn your oven on, you have a certain temperature, and the homeostatic device is the thermostat, right? You open the door, and then it automatically goes back up to where it needs to go. In this case, it's a reliable system that automatically maintains its reliability by handling negative perturbations in a way that, therefore, they no longer have a negative impact.
Yeah.
That's what I'm saying. And it seems like you guys are building the type of infrastructure where maybe someday that would be possible. Maybe not. I mean, it's just
That would be
like
great.
some fancy
Yeah.
operating system isn't dead. Research is alive.
No, but you know, that was one of the things that's really the best about Singularity is that it's really a laboratory for doing this kind of experiment. You know, a real commercial operating system is a very big piece of code. It's very hard to change. It's very hard to do any kind of experiments with. And similarly for most applications. And so, you know, one of the beauties of Singularity is that it's a reasonable sized code base, and it probably will be because we can't write code that fast.
Yeah.
And it's hopefully well written, and the people who've written it are around. And so we can actually do experiments. So, you know, if someone comes along and wants to build a homeostatic operating system and has some good ideas, you know, this is a great place for them to start because they can actually stick it in to the kernel, and you know we'll have stuff running on it. They can actually evaluate the ideas in a reasonable context, and you know, then they'll have some evidence for whether it's a good idea. They'll understand when it works, when it doesn't work. You know, they'll maybe be able to sort of evolve the idea before they actually try to apply it in a more real system or more real context.
That's a fantastic point. So it's really, Singularity is primarily a tool for understanding, a conceptual tool, a framework
Yeah.
for understanding operating systems.
Yeah, that's a good way to put it. Yeah, and it's, you know, there's no, one of the benefits is a research platform is there's no taboos. There's no, you know, if you say, you know, I want to change the way processes work, or, no, I don't think we need a file system. I've got some other wild ideas. Well, it's pretty easy in this environment to do it because it's so malleable and it doesn't matter if you break compatibility.
And so if someone came to you and said, you know what, I don't like the idea of threads. Let's do something else. You say, okay, fine.
Yeah.
Come up with it, and you can use Singularity to test it out.
In fact, we'd say, you know, great. You know, tell us how we can get rid of threats. You know, go and you know build some processes on Singularity that don't use threats and show us how it works. And you know, you don't have to change the rest of the system. Just show us some of it, and if it's a good idea, we'll build it into the system and we'll use it ourselves.
Who are the leading thinkers in OSs, maybe even outside of Microsoft? Who do you look up to?
We're looking at it.
Well, okay. Other than you, you know, I mean, research, right, doesn't happen in a vacuum, and you paying off of other people, and I'm sure other companies are doing some research, not as much as maybe here, but you see other, you know, who do you look up
There are a
to?
bunch of you know really excellent researchers in universities who worked in the area of operating systems for a long time. I mean, you know, MIT has always been a perennial powerhouse in terms of operating systems. There's been good work across the lake at UW as well, and they're doing some very interesting stuff these days as well. You know, some of the operating systems people have drifted into other areas. You know, for instance, Dawson Engler at Stanford went into the software tools area. And, you know, other operating systems people have gone into distributed systems or sensor networks or, you know, the other sort of more newer areas. I guess I was going to say more exciting, but I'd say newer instead. So there are a lot of really good people out there. There hasn't been a lot of research activity in operating systems in the past couple of years. I think, you know, people tried a bunch of ideas with the microkernels, and then, you know, the internet came along and sensor networks came along, and they sort of went off in different directions. And, you know, I think what Galen and I are trying to say to the community is it's time to come back. You know, the problems that we're bringing up in terms of system reliability and extensibility and you know, taking advantage of the advances in languages and tools are open problems, right? They're things that the community really hasn't solved. We don't know how to build a robust, reliable operating system that's going to just sort of run without any maintenance and is going to be secure against bugs. Nobody knows how to do that. It's not us, it's not Linux, it's not Unix, it's not some small company someplace, and the techniques just aren't there. And you know, this is important, right? Because everything is built on top of an operating system. And so, you know, if you sort of start with an operating system, any operating system that has, you know, drawbacks to it, then everything that's built on top of it is going to be on a shaky foundation. And so, we're saying to the community, come back. Let's see if we can't come up with some better ways of solving these problems. Right? The techniques aren't there. They aren't in the commercial world. They aren't in the research world. It's time to do more research in this area.
Fantastic.
How has, over the last, 6 years since the internet really started taking off, how has that changed your thinking about what an OS is?
Well, I think
I think back to '95, back before the web really took over.
Netscape.
Pre-Netscape, pre-web,
Well, I think one of the fundamental ways that it's changed, at least given us the opportunity to rethink how we build an operating system, is the security model, right? So you look at the security model that we basically build into operating systems right now. The model that's essentially the model you have in Windows, Linux, Mac, Apple's operating systems on the Mac, etc. There's this fundamental security model, which is what the kernel tries to protect you against is between two programs from two users that have rights to use that machine, accidentally or maliciously interfering with each other. Maybe being able to write into your processing which you have. Okay. That's not the threat anymore. The threat now is code coming in from the outside that I, as a user, either intentionally run because I think it's going to provide me a service, or accidentally run because there's a leak that it gets in the system. And how do you protect the user against himself? Well, the security model that we have doesn't really address that problem very well, and that's why we have a lot of pain.
It's a really hard problem, right? It's protecting me against myself.
Exactly.
And Java tried to do this, right? Java came in and said, we're going to have this really fine-grained security model so that you can sort of say this little applet that you downloaded doesn't have permission to do this and that and some other thing. But, that ended up being a very difficult model because you couldn't really sort of enumerate all the things you really did or didn't want a little piece of code to do in all circumstances. And so you ended up with these sort of broad categories that sometimes worked. And the implementation was really complicated. There were lots of bugs in it. And, what we're saying in Singularity is, well, if you don't trust code, then maybe you ought to be able to run the code that you don't trust in a very isolated way and really sort of see the interactions of it. And, maybe, stuff that you don't trust, you shouldn't be sort of loading it into your world and then trying to impose very fine-grained protections on it. So, we're taking a very different approach. We're sort of going the opposite extent and saying, let's not trust anything. Code that, we download from the internet, code that's an extension like a device driver that you load on your system, and let's see how far we can go with that, as opposed to sort of starting with the other assumption, which seems like a bad assumption these days. Maybe, 10 years ago when Java was getting started, the world looked a little different. We didn't see quite as many malicious pieces of code floating around.
And we were probably naive. We didn't think that the internet would be full of sharks.
Right. We didn't even have advertising back then.
Yeah. That's true.
The good old days.
Good old days. I'm thinking of, in the future, my devices are going to know about each other and react to each other in some way, this camcorder has a computer in it. It has no clue about the desktop computer underneath your desk. Has no clue if I had a stopwatch on or a cell phone or... and I think that's going to radically change in the next 10 years, where these devices are all going to know about each other and change behavior based on proximity or other things.
Right, but you're going to need real security for that, right? Because whatever communication your cell phone's going to use with that camcorder, the guy outside with the cell phone may be able to do it too.
Yeah.
And, we have to be able to distinguish your cell phone from my cell phone or Galen's cell phone. And so fine-grained security is going to be important.
Well, and identity, Kim Cameron,
which is still being worked out.
Yeah.
Right.
There's a lot of work to do.
Yeah, there's a lot of work. The networking really sort of changes your view of the world. You can't sort of say I'm an island, and I don't have to really worry about security except for people I let into the island. Because if you're really on the mainland, then a lot of people can walk through your piece of ground.
It's interesting. So it's sort of, you need like kind of a gatekeeper. So you let a process in, or you let some code in, but you run it, as you're saying, in a protected way, and the operating system maybe runs it in the background and says, oh, it's trying to do this. I know exactly what it's doing because it's running it. I'm evaluating it. Yeah, you can run it. Or you can say, you can have a setting that says, okay, always make sure that the stuff I'm running is safe. For example, doesn't try to delete my hard drive, because an operating system could be smart enough to know that.
We can only trust code that was written by Galen.
We're in big trouble. That's it. So that's the thing. We don't believe in distrust. We believe in verify.
Yeah, it's true.
The only reason why we like Galen write code. But this actually hits on one of the really, I think, one of the interesting opportunities and one of the things we've done in Singularity, which is we say that all of the code that comes into your Singularity device has to be expressed as MSIL. We have this intermediate language between what gets delivered to the desktop, if you will, and what the instruction string is that we feed to the processor. Okay, so one of the things, we've got a level of abstraction there where we can talk about, say, this is a piece of code. I don't know about this, whether I trust this piece of code, so we can insert extra security checks and really heavily monitor that piece of code. But then after let's say you know who wrote this code, you trust it, well, then you can run an environment where you say, I want to optimize everything I can. Take out all the security checks, because I know I'm going to run it, say, behind a firewall, and I know who wrote it, and a bunch of other things. And so you have this now, an opportunity, you can make this trade-off. Whereas if you look at your system now, you go buy a copy of SQL Server and run it on a computer, you can't make these kind of trade-offs, because the binary, the little code that's going to run to the processor is the code that you receive on the CD. Whereas in Singularity, there's this level where we can, in a sense, to me, it's kind of completion about what operating systems were about. Operating systems are about virtualizing physical resources and idealizing them and abstracting them so that we can, provide developers with a saner foundation than the real hardware to run on.
Sure.
And for the first time, in a sense, we've brought the processor, the instruction set, into that fold of managed devices. We used to manage the processor from the perspective of timing. We can interrupt it and make it run another piece of code. But now we can actually virtualize the entire string instructions.
And it also sounds like you're virtualizing software for the first time, in the sense that you're now providing a mechanism where, since MSIL, you could also figure out exactly what that code wants to do, precisely what it wants to do. Could you not?
Well, there are limits.
That's an interesting question.
There are limits to how precisely you can know what code's going to do. Right? I mean, because there's always the Turing halting problem behind this. I mean, we can't even answer a fundamental question whether this program's ever going to finish executing. And it turns out, because you can't answer that question, lots of other questions that you might be more interested in, like, is this program ever going to, delete a file on the disk? You can't answer those questions in general as well. This is the sort of gotcha behind all the program analysis, is that there's a really hard, unsolvable problem behind taking a piece of code and looking at it, deciding how it's going to behave under all possible circumstances. But, we can do pretty well, and you can do things at runtime that you can't do statically in advance. So, as Galen was describing, if you don't trust a piece of code, you can run it in a really paranoid environment where sort of you're checking things, and it's really easy to tell whether it's about to delete something on the disk, because there's going to be a message that it sends saying delete a file on the disk. And so if you don't want it to happen, you just don't let that message get through. And, really what we're talking about is giving the operating system another level of mechanism for imposing whatever policies you want. So, we can not only sort of look at the interfaces to the system, but we can actually look at the code and sort of impose things in there, either things that observe what the program is doing or actually even change its behavior. And that imposition is under the control of the operating system. So it's a new way of having the operating system enforce whatever policies you want. So they can be security policies, they can be performance policies, they can be, various other things that you would like to have uniformly done on your system.
Fantastic. Yeah. Well, sounds great.
Very interesting project.
Very interesting.
We've been having a lot of fun with it.
What's the next year for Singularity? What would you like to try out that you haven't tried out yet?
Well, I think actually the next year, we're going to basically take what we have, and we've got to make it much more robust in a number of dimensions, in terms of having the performance be a little better, have the code be a little bit more general and reliable, so that we can get more people involved in it. Right now, we've had a sort of kernel of people writing the kernel, and there are a lot of other people who have been involved in the discussions who want to come in and start trying out their ideas for security, their ideas for networking, their ideas for file systems and things like that. So, to get to that point, we actually sort of have to have something where they can use it without sort of it breaking or them coming to us frequently. And I think over the next year, what I see us doing is taking what we have and making it sort of more robust and reliable, and then having lots more people get involved and start pushing the research in many different directions. For instance, my group is very interested in taking some of the software tools we've been working on for 6 years and applying them to Singularity to start finding errors using static analysis. And we've got now a fairly large, fairly interesting code base, and so that'll help drive the tools research because it'll let us try out the tools on reasonable size, tens of thousands of lines and pieces of code, and sort of make those tools better. But at the same time, it should help us find some bugs and make Singularity more reliable. So that's the sort of interlock synergistic research that we hope to do in a number of different areas over the next year.
One of the I just met with the build guys over on Longhorn team, and just to compile Longhorn takes, I think, 3 to 5 hours on a really, multi-million-dollar machine, and 7 hours on a $30,000 machine. Do you ever see the time where you don't need to compile an entire OS every time like that to build it, where you could, compile a piece of it, or would your system,
I don't think we've really sort of looked at doing that very much. The people who write the system were complaining this morning that ours takes too long to compile.
It takes 6 minutes to build right now.
It takes 6 minutes to build.
Okay,
Small.
so right there, that gives you an idea of really how small our system is,
Sure.
how much functionality it is. It's just a prototype, right? But
But people still complain about
we still
6 minutes.
complain about it. Oh, yeah.
Now, do you have people in the user interface research world that might want to build a shell for this thing and play around with what it would be like to write
Not
a shell
yet.
on top of that?
No one's expressed any interest in doing that.
Okay. So fair enough.
For now, it looks like DOS.
Fine. Interesting.
We do have a web server, though.
Wow.
You can't have an operating system and not have a web server.
A managed web server.
Yeah.
Yes.
Fantastic.
Yeah.
So you parse HTML and that kind of stuff?
Uh-huh. Well, HTTP. I mean, it looks.
HTTP, well, I mean-
it's a dynamic web server. There's a web server called Cassini that was part of the Rotor system, and we actually had one of the devs ported Cassini to run on top of Singularity, and then added the software isolated processes for the dynamic content runs as separate process, these separate isolated processes.
make it to a blog, and you got something.
Operating system that's just a blog interface. That's the shell. That's the blog.
Yeah.
I've never written a blog entry, so I don't know how to
Jim and I are showing our age.
Yeah, make it spit out an RSS feed, and we're all happy.
You guys go to host your Planet Mind.
That's it. Have it deal with WMD files and RSS, and you got something to run Shell 9.
There we go.
Well, this was great. It's been nice to meet you, and very good luck on your project. Sounds very interesting, and hopefully it'll get larger with even more interesting components and people testing on the platform. That's cool. And it's not a product. We won't see it anytime soon, but it's a great research tool. And viva the microkernel.
You know the microkernel.
All right. Thank you, guys.
Thank you.
Appreciate you.